Yes, yeah, am I audible?
Yes, sir.
Are you able to see the screen?
Yes, sir. Visible, sir.
Okay, right, right. Yeah. So, yesterday we discussed about the chemical shift and the factors affecting on the chemical shift here, right? So, here the factors, some factors are affecting the chemical shift values here because the general scale of the C13 is 0 to 240 ppm here. And based on the based on the factors, the value is going to vary, right? So here the factors which are listed like electronegativity, hydrogen bonding, steric factor, and solvent effect here, and hybridization. Right? So all these are the factors which are affecting the chemical shift values here, right? So due to presence of these factors, the value sometimes the value may be increases or will be decreases here, right? For example, if you take the electronegativity, so the electronegativity it is directly proportional to the chemical shift values. That means if the electronegativity is increases, the chemical shift value will be increases here, right? So like for example here the carbon, when the carbon is attached with the uh, fluorine, okay, means the same carbon, we are taking the same carbon, but we are attached the different electronegative atoms like chlorine, fluorine, and bromine here. Then the carbon chemical shift value is going to change, right? So you can see the different chemical shift values of the carbon. Means here in three cases, the carbon is same. Only one carbon is there, but only thing is that carbon is attached with the different electronegative atoms, right? And if you see the order of the electronegativity of various carbons which are attached with the halogens here, so the carbon attached with the fluorine is having the higher delta values here, chemical shift values. And then the carbon which is attached with the fluorine is having the next means it is uh, less than that one. Then the bromine attached to carbon is it is having the least value. Means we are comparing only these carbons when attached with the different halogens here. Okay, so like that means this change is the difference in the chemical shift values of these three carbons is due to the attachment of the electronegative atoms here. Okay, so like that here with increase of the electronegativity, the chemical shift values of the carbon is going to increase here. And here the hydrogen bond, for example, right? So then what happens here? The hydrogen bonding is increasing the chemical shift values. Okay, because here the hydrogen bonding when it is participated, right? So when it is participated in the hydrogen bonding, so it leads to decrease the electron density on that particular atom here. Okay, so when the electron density is going to decrease on the specific atom here, then it is showing the higher delta values here, right? So because it is inversely proportional, the electron density is inversely proportional to the chemical shift values here, right? So like that, all these are we discussed in the last class. Means yesterday we discussed all these things here. Now we'll see the coupling constant in the C13 spectra, right? The couplings and the coupling constants values we'll see in this one. Right. So the coupling means the mutual interaction. Okay, the coupling nothing but the mutual interaction of the atoms here. Okay. So here in this couplings, the interaction here, we have two categories, right? So we can classify these couplings in the C13 spectra uh, as the two categories here. One is homonuclear couplings and the heteronuclear couplings here, right? So here the homonuclear coupling means where the coupling are the interaction between the carbon and carbon. right? So like in the proton NMR spectra, with the homonuclear coupling, with the coupling between the hydrogen and hydrogen. Same thing here also. The homonuclear couplings involves the interaction of the carbon and the carbon. And the second category is the heteronuclear couplings here. So heteronuclear couplings means the coupling between the hetero means the different, isn't it? The hetero means the different here. So the coupling between different atoms. Okay. So that is the heteronuclear coupling. So this is further classified into two types here. Here is a coupling between the C13 and the hydrogen. Okay, the coupling between the C13 and the hydrogen here. So when the carbon is attached with the hydrogen, then you can see the carbon-hydrogen coupling. And the next category of the heteronuclear couplings, which is seen in the C13 spectra, is the coupling between the carbon and other magnetic nuclei like fluorine, okay, and chlorine here, chlorine, and phosphorus, right, and sulfur, all this. Okay, based on that attached atom, we will have the category of this heteronuclear couplings here. When the carbon is attached with the fluorine, we have the C13 and F19 coupling here. Okay, and when it is attached with the fluorine here, you can see the C13 and P31 heteronuclear couplings here. And when it is attached with the nitrogen, for example, then you can see the C13 and N15 couplings here. So like that, based on the nuclei which is attached with that particular carbon, we are going to classify the kind of the heteronuclear couplings, right? And homonuclear couplings, generally it involves the coupling between the C13 and C13 here. And generally this heteronuclear couplings in this carbon 13 spectra is very less common here. And heteronuclear is common, and homonuclear couplings are very less common here, because here the C13, okay, the C13 nuclei, right, the finding of the C13 nuclei adjacent to that carbon is, it is difficult here, right, because the abundance or the availability of that C13, or the natural abundance of the C13 is, it is 1.1 only, right? So it is very difficult to find the same kind of the nuclei in one atom here. That's why that you can see that these homonuclear couplings of the C13 and C13, it is less common. And if it is found, so very weak interactions are possible here. Okay. First, we'll see that one bond couplings here, right? So first we see the heteronuclear couplings, the coupling between the carbon and hydrogen. So based on the intervening bonds, right? The intervening bonds mean the bond separation. Okay. So here, uh, yeah, right? So here the intervening bond, here is this is carbon here, and this is hydrogen. Okay. So this is the carbon, and here is hydrogen here. And these carbon and hydrogen separated with this bond. Okay. So one bond here. So one bond separation. Then it is called the one bond coupling, right? So here this bond is called the intervening bond. Okay, it is called the intervening bond here. Means the bond between the two separated atoms is called the intervening bond. Okay, intervening bond here. So if one intervening bond is present between the two hetero atoms here, then we call the one bond couplings. And generally here, the one bond couplings, these are very common in the C13 spectra here. And here, if you see this particular, the one bond coupling is depending on the S character, the values, what is it, the chemical shift values is depending on the S character, right? So the coupling constant J. So what is J generally here? the coupling constant. So coupling constant, nothing but the separation. Okay, J is nothing but the signal separation here, right? So in the, for example, you can see in the graph here, right? So if we have these two lines, right? So here the separation between these two signals is called the J, right? The separation between these two is two signal is called the J here. J nothing but the coupling constant, right? So and generally the J, the coupling constant, also it measured in the heads here. Okay, same as what is it? In the H1 NMR spectra, the coupling constant is measured in the heads here. Now you see, and this coupling constant is depending on the S character of the hybridization, right? So here for example, in the methane, S character is 25% because it is sp3 hybridization. It involves in the sp3 hybridization. So the S character is 25% and remaining 75% is P character. Okay. Then it is that's the coupling constant value is it is in the range of the 125 Hz. And it is if it is in the ethylene, right? So in the ethylene, where the S character is increased. Okay. So it is increased from 25 to 33% in the sp2 hybridization, right? So in the ethylene, you can see the sp2 hybridization. Right. So here in the methane, you can see the sp3. Okay. You can see the sp3 hybridization. And in here, you can see the sp2. And here you can see in the acetylenes, you can see the sp hybridization. Okay. So here in the sp hybridization, you can see the 50%, 50% of S character and the 50% of the P character here. Right. So where the S character is going to increase, then its value is going to increase here, like 250 heads here. And in the ethylene, you can see the S character is 33%. So it is more than the sp3, uh, right, J value, and less than the sp J value, right? It is medium, moderate values. Okay. And here yeah. So with increase of the heavy atoms in that particular compound, the J value is going to increase here. Coupling constant value is going to increase in the one bond separation compounds here, right? So in all these compounds, you can see the one bond separation here. Okay, short range one bond separation. It is short range couplings here, right? So generally the weak means long range couplings is there, but the long range couplings are very weak couplings here. So in the short range coupling, in that the one bond separation, so we can see that, for example, here in the methane CH4, the coupling constant value is 125 Hz here. There is no means what is a heavy atom in this particular compound, right? So it is purely the carbon and hydrogen elements are present. So the chemical shift value is it is 125 Hz. And when the one of the hydrogen from this methane is replaced with the chlorine, then it becomes methyl chloride. Then what happens here? The J value is going to increase because we substituted the hydrogen with the chlorine here, one chlorine. Then it is going to increase from 150, 125 to what is a 125 to 150 here, right? So that there is a increase of the 25 Hz value here, 25 Hz. Then we are substituted one more chlorine here, right? So we are substituted the two chlorines there. Then what happens here? Again, you can see the some right, some increase in that H what is that J value, chemical what is it, coupling constant value, right? Now finally we are going to replace this particular one more hydrogen with the chlorine. Then we are substituted three chlorines here. Then you can see the more increase in the chemicals, sorry, coupling constant value, like it is 209, right? So without chlorines, the electronegative atoms here are the heavy atoms. You can say it is heavier atom, If there is no heavier atom, then the value, the simple methane is having 125 J value. And upon substitution of the hydrogens with the various numbers of heavier atoms, then it is going to increase the J values here, right? So like this, where that particular, right, the J value is going to changes according to the substitution of the different electronegative atoms on that particular carbon attached hydrogens here. Right? And here also you can see in the various right, the change in this particular J values depending on the substitution of that particular electronegative atoms or the electron withdrawing groups here, right? So when it is in the simple alkane, okay, CH3CN, methyl nitrile, so the value is 136 heads here. And when this nitrile group is attached to the sp2 hybridized car, here is the cyanide, the nitrile is it is going to it is attached on that particular sp3 hybridized methane here. Then the value is 136. Okay, and when it is attached to the sp2 hybridized the ethylene molecule here, then the value is going to increase by 177 heads, right? So means here what happens here, where the S character is going to increase from the methane to here the ethylene, the S character is going to increase here because here sp3 you know that the S character is 25%, and in the ethylene where the S character is, it is how much it is 33%, right? So where you can see the increase in the J value here. Now we'll see the two bond couplings here. Earlier we discussed the one bond say separation, means one bond coupling. Means one bond coupling means like you can say it is geminal coupling. Okay, uh, but here is the two bond couplings, right? So here is a vicinal coupling. Okay, the geminal coupling means where on the same carbon when the hydrogens attach on that particular same carbon here. Here is the vicinal coupling. We can say it is the vicinal coupling. J2 here are two, right? So here the two indicates this particular on the suffix. Okay, superscript I think it is, right? The superscript two is it is called as a, right, the number of intervening bonds here, right? That's two indicates the number of intervening bonds. Intervening means the what that particular separation. Okay, right? So the bond separation here. So how many bonds means the atoms separated by how many bonds is called the intervening bonds, isn't it? So now you see here that the two means there is a two intervening bond between the terminal or the coupling atoms here. Okay, so you see here this carbon, right? So this carbon is and this hydrogen. This carbon couples with this hydrogen. You can see the heteronuclear. The coupling is a heteronuclear, not homo, right? So it is a heteronuclear coupling here. And heteronuclear coupling is coupling involvement atoms is separated by the two bonds here. This is one bond here. This is another bond. Total there are two bonds. So we mentioned the superscript as two here. If you mention the superscript as three, then it is three bond couplings, right? Or the three bond separation. So based on the number of intervening bonds, we are mentioning that value on the superscript of the J, right? And here you have to mention which atoms are involving in the coupling. Okay, so when you are writing that particular couplings here, when you are mentioning of the coupling, so you have to mention which atom are, right, involving in the coupling. For example, if you mention the CH here, okay, then it indicates the coupling is involved in between the carbon and hydrogen. For example, if you mention that chlorine, you mention the phosphorus here, okay, then the coupling between the carbon and phosphorus. And on the superscript of this J, you have to mention that the value. right? So which coupling is that? Whether it is one bond separation or a two bond separation or a three bond separation, that thing you have to mention, right? For example, if you mention three here, then it is three bond separation. Three bond means we call these bonds as the intervening bonds. Okay, so there are two intervening bonds here, so it is a two bond coupling here also. And yeah, and we think upon substitution of the electronegative atom on that particular carbon, the value is going to increase, the J value, right? The J value is going to increase here, right? So here the electronegative substitution increases the J value. We can see with this example here, you see this particular yeah, acetaldehyde. Okay, in this acetaldehyde, you can see that there is a, okay, so here the coupling of this carbon, right? The aldehyde carbon and the hydrogen here. Okay, C2 carbon. This is C1 carbon. This is C2 carbon. Yeah. So here the carbon, the coupling is involving between the carbon and the C2 hydrogen. Right. So where then you can see the where the two bond coupling, the value is 26.7 J value. Right. The J value is 26.7 Hertz. Then what in the next example, just you see, we are substituted the one of the hydrogen with this chlorine, right? So on this aldehyde group here, we have substituted the chlorine here. Now we are where this hydrogen in this the chlorine substituted carbon are involving in the, right, involving in this particular what is that coupling, right? So then you can see the value, right? It is going to increase 32.5, right? So well, there is an increase in the value here. And in the next example, just we have substituted one more chlorine here, right? So we have substituted two chlorines here. There is a monochloro, there is a dichloro, acetaldehyde. Then you see the value increased little bit bigger than that one, like 35.3. Okay. And in the aromatic compounds also you can see, right? So here the acetylene compound, right? Like the acetylene, which are substituted the methoxybenzene here, sorry, benzoxy, phenoxy, acetylene, and here is a acetylene is substituted with this particular the aldehyde group here, right? So the this particular benzene, okay, the aromatic, okay, the aromatic group, right? So it is electron donating group here. You see the methox. Okay. So because the oxygen is carrying the pair of electrons, it is going to, right. So right. So it is donating the electrons towards this particular, right. So then the it is involved. It is a plus I plus Me group here. It is a plus Me group as we discussed yesterday. Yesterday we discussed about the effect, mesomeric effect on the chemical safety values, right? So here the substitution of the semi group leads to increased electron density on that particular carbon or the atom. Then if the electron density is increases on the specific carbon, then what happens here? The delta value is going to decrease. Okay. So if the electron density is decreases, then the delta value is going to increase here. That is inversely proportional, right? The electron density is inversely proportional to that particular electron density, right? Chemical shift values is inversely proportional to the electron density. Now you see here the this particular benzene, right, which is attached with this oxygen, right? The ether, so the ether, aryl acetyl ether, Okay, so aryl acetylene ether. Then you see the value of 61 heads, right? So here also you can see the what is that? Two bond separation. Right, the coupling between the this carbon and this the terminal hydrogen, right? This internal carbon and the terminal hydrogen here. Then the value is observed as 61 heads here. Now, when this acetylene is attached with the like aldehyde compound here, then you see this is a withdrawing nature, right? Where this oxygen is a donating plus Me group here, and this aldehyde is minus Me group. Okay, so minus Me group generally it leads to means it is attracting the electron. It is decreasing the electron on that particular carbon. Then what happens here? Okay, so it is because right. So due to the polarization of this pi bond on this oxygen here, right? So this is going to polarize on this one. Then the electron density is going to decrease on this particular carbon because it is attracted towards this CO bond. The bond electrons are attracted towards this bond electrons are attracted towards this are polarized towards this carbonyl group here. Here is okay. So then what happens here? The density, electron density means the deficiency is created, right? The deficiency is created. Then the density is electron density on that particular carbon is going to decrease. Then the value is going to increase, J value, right? J value is increases as well as your chemical shift value also increases because the electron density is inversely proportional to the coupling constant as well as the chemical shift value, right? So here you can see the 33, right? Now here the three bond separation, right? The three bond coupling here. So three bond couplings. Here you can see the intervening bonds, right? There are three intervening bonds here. One, two, and three here. Three intervening bonds, right? And generally here, with increase of the number of intervening bonds, right? With increase of the number of intervening bonds, the coupling constant value means the coupling becomes weaker here, right? It is becoming very weak. So you can see very weak interaction, right? Because the atoms are very far away, right? So the value is going to means right. So the when the distance is increases, right? The spatial separation between the atom is increases here. Then the value is going to decrease here. Now you see in the aromatic compounds, right? So here this the dihedral angle, right? The coupling between the hetero atoms like carbon and hydrogen in the aromatic compounds that is depending on the dihedral angle here. Now you see the various cases observed when the dihedral angle is 180, right? Then the J3 coupling, three bond coupling is maximum, right? 180 means where on the opposite that the both are means the coupling atoms are in the opposite direction here, like para position, for example, right? The 1-2 para, 1-4 position here in the aromatic. If you take the aromatic substitution, the benzene here, 1-4 position, that is 180 degree, that angle between that, right? Next, when the dihedral angle is zero, the J value is it is less than the maximum value. Means it is less when the J value is zero here. Zero dihedral angle is zero. That means there is no means both are overlapping here. Okay, so where the atoms are overlapping. Next, dihedral angle is 90 degrees here. Then it is minimum. Okay, so uh, here you see the example of this substituted benzenes here. You take the chlorobenzene, right? So in the chlorobenzene, here the you can right. So one chlorobenzene here. So you can see you can observe the coupling between the carbon and hydrogen here, and what will be the J values, right? The change in the J values, you can observe the scenario of this changing of the J values, right? For example, here when the C1 carbon here, that is C1 carbon means the carbon attached with chlorine here. C1 carbon is involving with the C3 hydrogen, right? C1 carbon here, the coupling, right? Because here it is, right? So here the hydrogen is there, right? So it is a three bond separation, right? Coupling here, long range coupling. Somewhat it is long range, not it is a short range. So here this carbon and this hydrogen is in the coupling here, right? So you can see the intervening bonds. This is one, this is two, and this is three. Right? There are three intervening bonds. That's why it is J3. Okay, here the three is mentioned on the superscript to this J. So when this C1 carbon involving in the coupling with the C3 hydrogen here, the heteronuclear coupling, then the value is going to right noted as 11.1 here. Okay, and C2H4 here. Here the C2. This is the C2 carbon here, and here is a hydrogen. Okay, so when this coupling is takes place, then the value is going to means it is mentioned as 1.9 here, and then C2H6 here, yes C2 and the H6 here on the reverse side, anti-clockwise the coupling. Okay, so when you can see the value is it is 5.0 and C3H5. Okay, so here is a C3 carbon and the H5 carbon here, hydrogen here. Now you see clockwise. It is 8.2 here. Right? Now you can you can compare the values, right? The various couplings in the aromatic fluoro substituted aromatic benzene, like chlorobenzene here. So when the C1H3 coupling is takes place, the value observed is 11.1 here. Then the C2H4 is takes place. The value observed is 7.9. Right? So there is a more difference here. Right? So it is 4 point something which difference is there. Right? So that is why we are seeing this major difference or the large difference here is because this atom, okay, the carbon, C1 carbon is directly attached with the electronegative chlorine here, isn't it? So as we discussed in the above, right? So the electronegative attachment of the electronegative atom, the it leads to increase the J values here. So as per that statement, so you can see this change in the values. And then C2H6, you can see the very less, right, the value. C2H6, there is no electron C2H6 here. Okay, so there is no, right, electronegative atom attached on either this 6 carbon or the 2 carbon, right? So like that, you can see the impact of that particular electronegative atoms on that particular the J values. And same one disubstituted fluorobenzenes. Also, you can see the same this you can observe. Right? So when the atom is directly attached with these chlorines, then you can see the higher delta means the J values, coupling constant values. Right? Right. Now we are moving to this particular homonuclear couplings. As I told you, here this C13 isotope, right? So the finding of the C13 is it is very less like 1.1. Right? The natural abundance of the right, the natural abundance of this C13 element is 1.1 percentage here. So very minute, very negligible percentage is observed here. That's why the Homonuclear couplings means like C carbon-carbon couplings are very less common in C13 spectra here. Right here we see this, for example, one bond separation. Here also we can see the one bond separation, like separation between the carbon and carbon. So here we mentioned the one on the superscript of the J, and the coupling elements, means coupling atoms are carbon and carbon here. Right? And here the values you can see. Right? So this is the coupling uh, coupling in the C13 spectra. Now we will see the chemical shift values of the chemical shift values in the C13 spectra. Right? So here, so like generally here the chemical shift definition of the chemical shift is the absorption position of the signal with reference to the reference compound here is called the chemical shift, right? The absorption position. So in the 2D graph, right? So generally, all the spectra you can mention, right? Means it is drawn as a two-dimensional 2D graph only, right? So on 2D graph, so we have two dimensions. We have only two coordinates, like x coordinate and the y coordinate here. So on x coordinate, we'll take the chemical shift values here, beginning from the TMS. TMS is always taken as a zero. Okay, the TMS chemical shift values always it is taken as a zero in the C13 spectra and what is that H1 NMR spectra here, because it is chemically inert compound here. Okay, and the minimum is a zero and the maximum is it is 240. Okay, it is 240 here maximum, because all the means all the groups or the compounds will be all the right the carbon compounds will be uh, falls in this range only, but only the when it is a tertiary carbocation. Okay, so tertiary carbocation, so its chemical shift value is 334 ppm here. It is an exemption, right? Exemptional case here means it is beyond that scale, right? So for the tertiary carbocation, so you can it is appeared at 334. Okay, right. So the rest all the groups falls in this range only, right? So here the if any signal is appeared in the 2D graph of the C13 spectra, and generally you know that here in the C13 spectra you will see only the line spectra, right? So means like it is contrast to the H1 NMR spectra. In the H1 NMR spectra, you can see the multiplicity here. Okay, triplet, quartet, and singlet here, doublet. So that signal multiplicity will be observed in the H1 NMR spectra. But in the C13 spectra, there is no splitting pattern, right? There is no splitting pattern. You have only the lines. If there is a multiplicity here, then you can see the lines adjusted to that one here. This kind of pattern is observed in the C30 spectra, as we discussed in the offline, like right in the types of C30 spectra. We have the what is that BBD spectra? Okay, BBD spectra, OFD spectra here, and what is that selective decoupled spectra, right? So BBD spectra means generally there is all the means couplings are right homonuclear or the heteronuclear couplings are removed here. So you can get one signal for each carbon here. There is no CH couplings here. right? So the number of carbons equal to the number of signals, number of lines one, that is BBD spectra. In the OFD spectra, where you can see what is that, the coupling between the hydrogens here, right? So if there is a two hydrogens attached to that particular carbon here, then you will get the n plus 1 here. N equal to the number of hydrogens attached to that particular carbon. Okay, then you get the N, for example, it is a CS2 group. Then you get the triplet, means three lines here, like this, not like this here, right? In the proton NMR, there is a CS2 group here. Okay, so in the proton NMR spectra, if there is a CS2 group, so you will get this kind of splitting pattern. And in the C13 spectra, if there is a CS2 group, in the OFD spectra, you get this kind of lines here, right? So this is OFD of resonance, okay, spectra, OFD spectra of resonance, selective sorry, of resonance, decoupled spectra, sorry, coupled spectra, not decoupled, of resonance, coupled spectra in means C13, right? So like, and yes, you see the values here, the chemical shift values in the C13 spectra, various groups, functional groups here, right? Like here the carbonyl group, if the carbonyl is a part of the ketone here, the value is going, it is mentioned as 205 to 220. Okay, so it is, or you can take it as well, right? So 210 sometimes it is up to 220, you can see, right? In the general value, it is 210, and sometimes due to the factors, right? So due to the some presence of the some groups here, the values, it is extended up to 220. Right, so the carbonyl group, when it is in the ketones here, the value is 205 to 220, depending on the factors or the groups here. And when this carbonyl is in the part of the aldehyde here, then the value is mentioned as 190 to 200. Okay, and the carbonyl is in the acid or the ester. Okay, so the carbonyl group can be present in the aldehyde, ketones, carboxylic acids, esters, amides, and acid chlorides here. In all these, right, functional groups, you can see the C double bond O group, right? So when this C double bond O is present in the various functional groups, the value is mentioned here, right? So for example, when the CO is in the ketone, the value is 205 to 200. And the value is, which is CO is in the part of the aldehyde, right? So it is 190 to 200, right? And here you can see in the carbonyl, when it is in the part of the carboxylic acid or in the esters, the value is 120 to 185. And in the aromatic ring for benzene here, you take aromatic benzene ring, the value is up 125 to 150 here. And when it is in the means alkenes 115 to 140, right? So in the aromatic also, we have the C double bond C, and in the alkene also, we have the C double bond C here. But the value is, you can see some difference, right? So because in the aromatic, it is in the cyclic form here. The double bond, C double bond C are the cyclic form here. And in the olefins or the alkenes, it is C, right? Acyclic open chain nature. This is the chain nature. And you know that the bond angle, right? So when it is in C double bond C, the bond angle is how much it is? 1.34. Okay, the bond angle is 1.34 angstrom. In the C double bond C, the bond angle is 1.34 angstrom. In the alkenes, when it is in the alkenes C single bond C, it is 1.54. Right? C single bond C, it is 1.54. And C triple bond C, it is 1.20. And same thing when this C double bond C is in the aromatic, right? So in the aromatic C double bond C, the bond length is 1.39. Okay. So the bond length is 1.39 angstrom. Okay. So when the C double bond C is in the alkene, the bond length is 1.32. The C double bond C is in the aromatic here. The bond length is 1.39 angstrom. So this bond length also one of the factors which is affecting the chemical shift values here, right? So because we have the same, right, C double bond C nature, but the you can see the difference in the chemical shift values. The difference is due to the change of the bond angle, bond length here, and the bond angle also, so it is different, right? So due to this one, we can see the in the olefins, the value is 150 to 140, and in the alcohols, okay, aliphatic alcohols, the value is 50 to 65, right? So these values are very important here in the practical uh, right, point of view, correct? And when this the primary alkanes attached with the chlorine, the value is 40 to 60. And it's amine, when the amine electronegative nitrogen containing amine group is there, attached to this primary carbon here, right? When the chlorine is attached to the primary carbon, the value is 40.45, 40 to 45. And when the amine is attached, then 37 to 45 here. So here the chlorine is a more electronegative than the nitrogen. So you will see the more increase in the value, more observed the value here. Now here the tertiary carbon, right? So for the tertiary carbon, the value is 25 to 35. Okay. And here the acetyl group, CH3 C double bond O. So for the acetyl group, the value is 20 to 30. And for this secondary carbon, right, the secondary carbon, the value is 16 to 25 here. And here is a primary carbon, 10 to means alkane, right? So in the alkane, for the primary 10 to 15. And in the alkane, the secondary carbon 16 to 25. And when it is in the tertiary, it is 25 to 35. Okay. But when it is the carbocation, tertiary carbocation, the value is very high. Okay. That is 334 angstrom. No, sorry, 334 ppm. Right. So in the means the schematic means mentioned of the functional groups you can see in this table. Now we'll see the some individual compounds, the chemical shift values, and the chemical equivalence of these compounds here. For example, here the ethane. So generally, the ethane there are two carbons here, two methyl groups are there, and it is a symmetrical one. Symmetrical. So then how many signals we get here? So we get one signal only because it is symmetrical compound. Okay. So it is symmetrical. The bisecting is molecule two equal halves here. So both the methyls are falls in the same chemical environment. So we have only one type of carbon. So you get one signal for this one. And here also the tertiary, okay, the tertiary alcohol. So you can see these three methyls are same, right? So these three are falls in the same chemical environment. So you get one signal for all these three methyls, and one more signal you get for this tertiary carbon, right? So this is B. This is, so there are two types of carbon, so you get the two signals for this. And in the benzene aromatic, there are three types of carbons. Okay, so this is also symmetrical one. Okay, so this dimethyl 1,4, okay, para methyl, another 1,4 dimethyl benzene. So this is also symmetrical one here. Okay. So then you see here is there are three types of carbons. So how you recount this? This is one carbon, the ipso carbon, one here, and this methyl is another two, and these four are same. Okay, this one, and this one. Two means two ortho and two para. These are same, right? So these accounts for three, right? So this is one, this is two, and this is three. There are three types of carbons, and this methoxybenzoaldehyde here, para-methoxybenzoaldehyde. So how many types of carbons are there generally? There are six types of carbons. So you get six signals for this, right? So here for aldehyde carbon, this is one. So it is not a symmetrical, right? So and this methoxy carbon, this is two here. And for ipso carbon, right, this is three. And here ipso carbon, below ipso carbon, it is four here. Okay, and this is five. Okay, five here, and this is six. And this side are same. These two are one, and these two are one here. So there are six types of carbons. Okay, so you get the six signals for this. And this dimethoxy, yeah, dimethoxy benzene. So here also as means like your right. So like you have this what is that dimethyl benzene, right? So here you get the two chemically non-equivalent carbons, right? So here not here it is three actually, not two. Okay, so why it is three? Right? For this these two there are one here. Okay, this was this is two. This is the other. So there are three. Okay, there are three chemically non-equivalent results carbons here. Right. So here the calculation of chemical shift values. So generally means to calculate means to find out the chemical shift values. Generally we will means we'll do the means we'll record the NMR spectra here, C13 NMR spectra. So by C13 NMR spectra spectrometry means spectroscopy here, right? So you can measure the value, you can get the values, but theoretically you can calculate the chemical shift values of the compounds by following some rules here, right? So manually you can right calculate the chemical shift values here, and the values are means the values obtained by this manual calculation, it is not exact values which are obtained from the instrument, but you get some near value get here, means calculated value. Sometimes it is having very less difference with the experimental value, like in the UV visible spectra, by following the Woodward rules and Fisher rules. Okay, so we have calculated the lambda max of values, right? So like homoannular diene and heteroannular diene and the enone chromophores here. So like that, here also you can calculate the chemical shift values of the carbons by following some rules here, right? So how to calculate the chemical shift values? Here for the calculation of the chemical shift values here. So we'll consider the right. So this formula, right? And this formula is different for the various functional groups here. For example, if it is a alkane, okay, so for the alkane compound, so we'll consider this chemical formula here. This formula to calculate the chemical shift values, right? So delta equal to minus 2.5 plus epsilon Na, right? And generally, this calculation is allowed only the simple compounds here. And this calculation, the manual calculation of this chemical shift value does not apply to the complex compounds here, right? So it is applied to only the simple compounds. Okay. Now we see the how to calculate and what are the increment values we have considered. So we can see here the minus 2.5 plus summation of Na, right? So the epsilon, this is summation here. The Na. So minus 2.5 is it is the standard value of the methane, right? For the methane CH4, we are taking the standard value, it is minus 2.5 here. Then here the number of additive A is the additive shift parameter. The attached groups here to this methane, the attached groups, okay, we are considering. And for this additive, okay, values, we have the means we are given the values for this one depending on its position. Position in the sense if it is on the whether it is on the alpha position or the beta, the gamma, the epsilon or the delta. So that is depending on that the values means the different values are mentioned. So by adding those values, we can calculate we can get the chemical shift values of that particular molecule. Now we'll see the increment values for these things. Okay, so for example, here this particular uh, carbon is at alpha, right? So like here, the CH methane CH4 value is taken as a minus 2.5 here, right? Then the number of means the after the CH4, if any carbons are there, then we'll consider the additional values here. For example, if that carbon is at alpha position here, alpha means the adjacent one, immediate to that one, right? So it's the additional value is taken as a plus 9.1. If it is at beta position, the value is considered as a 9.4 here, and gamma it is minus 2.5, and delta it is how much it is plus zero point 0.3, and epsilon it is zero point 0.1 here, right? Uh, Sorry, it is epsilon it is almost 1, 2, 3, 4, 5 plus zero point 0.1, right? Then sometimes in the branched chains, in the branched groups here, means branched alkanes, if the carbon is, when this particular, okay, uh, methane means carbon is attached to the tertiary carbon, right? Like, for example, you see, right? So this is your tertiary carbon, right? The tertiary carbon. and this carbon is a primary one, isn't it? This carbon is primary carbon, and this carbon considered as a tertiary pair. Okay, right? So this is considered as a tertiary. So when the primary carbon is attached to the tertiary carbon, so the value is taken as a minus 1.1. And when the primary carbon is on the quaternary carbon here, means here the one more carbon is there, then this is the quaternary carbon, right? So see one quaternary carbon, then the value is minus 3.4. So like that, here we are taking the values, considering the additional values to calculate the delta values. Here we'll see one example. We can calculate the lambda, sorry, we can calculate the delta value of this particular the alkane derivative here. So 3-methyl pentane. Okay, so 3-methyl pentane, which we are taken for the calculation of the delta value. Now we'll see there are okay. So the parent chain is consisting the 5 carbons, isn't it? 1, 2, 3, 4, 5. There are 5 carbons are there, and one methyl substrate is there on this C3 carbon, right? Now we are going to means substitute the values in that particular formula, minus 2.5 plus the summation of Na. Now we'll see here, yeah. So here is a minus 2.5 plus 1 into 9.1. So what is a 9.1 here? So we can see the table, above table here, the alpha carbon value, right? So here is one alpha carbon, right? So this is alpha, right? So 1 into 9.1 here. Then 1 into 9.4. 9.4 is for the beta, I think, right? So there is a one beta part, right? So here is right. So here is this is alpha, and this is your beta. Okay, and in this side also same. This is alpha, this is beta, right? Right. So here 1 into 9.1, it is alpha carbon, which we are considered, and 1 into 9.4, it is a beta carbon, and 2 into minus 2.5. So what is 2.5 here? Above you can see 2.5. It is a what is it? The secondary carbon attached to the tertiary carbon here, isn't it? So here this is the secondary carbon, no, sorry, tertiary carbon, right? So this the C3 carbon is a tertiary carbon, and the C4 and C2. Okay, C4. So this is your tertiary carbon here, right? And the C4, it is secondary carbon. This is also secondary carbon. Okay, so there are two secondary carbons attached to the one tertiary carbon, right? Then we are taking the 2 into minus 2.5. Minus 2.5, it is the value of your secondary carbon which is attached to the tertiary carbon here. isn't it? And uh, plus 0.3 into 1. So what is that here? 0.3 is a yes, epsilon carbon. I'm sorry, 0.3 is the plus 0.3. Yeah, 0.3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So here generally 0.3, this is the primary carbon attached to the tertiary carbon here, right? So here the values are some, right? So some displaced here. So generally plus 3 is this is for this one. That's right. So this is for this one here. Right? This is for this. Right? This beta is 9.94, 9.4. This is for this one. And this is this one here. And this one. Right. So here some value is missing, I think here. Okay. So generally, okay. Right. So here got the value that is means upon it means addition of all these values, we got the 11.3, right? So the additional value is 11.3, and the observed value, this is the experimental value, right? The observed value is 11.5, right? So you can see very slight difference between the calculated value and the experimental value, right? Yeah. Also, you can see the right. So you can calculate the values for all these compounds. Okay. Yes. Now we'll see the effect of substituents on the alkanes. Right. So here the chemical shift of alpha, beta, and gamma carbon in substituted alkanes depending on the electronegativity. Right. So generally, in whatever that compound is there, if there is a electronegative group, then generally it increases the chemical shift values here. Means that group is falls in the de-shielding region. Right. So here we'll see the functional groups attached to that particular carbons and their increment values here. If the acid group is present on terminal here, on terminal carbon, the value considered as a 21. If it is the right, the internal, in between that, right? So on the terminal carbon here, for example, right? So here is C, C, here is some carbon, and the terminal carbon is consisting the acid group here, for example. Okay, this is so this is a terminal, alpha terminal here. Okay, right? And for example, here CO overheads, right? So this acid group is not attached to the terminal carbon here on either side, this side or this side. It is internal. Okay. So this is internal. If the acid group is attached to the terminal carbon, then the value is taken as a 21 here. If the acid group is attached to the internal carbon, then it is considered as a 16, right? And if it is in the beta, right, this is alpha, this is beta here. So the beta carbon, the acid group is attached, okay, on the beta carbon, internal beta carbon, then the value is this one. If it is terminal beta carbon here, terminal beta carbon, then it is 3. And same thing the ester group, and here is a amide group here, right? So aldehyde group. So all these are the values mentioned for the various functional groups here. Okay, now we'll see this here, this particular alcohol, where this alcohol group is, hydroxy group is attached to the alpha internal carbon, right? So then the value is taken, for example, yeah, C3, C alpha in 3 hydroxy pentane here. So C3 alpha, how much it is you can see. Alpha hydroxy, where is that hydroxy? Yeah, this one. Alpha internal, not terminal. So it is 41, right? So it is taken as a 41 here, and the value is calculated. Okay, and these are the some other different groups, right? Taken for the calculation of the lambda maximum values. Sorry, delta values. Okay, all these are the exercise you can see. Now we'll see the aromatic here. Aromatic chemical shift values of the aromatic compound. And generally the aromatic compound chemical shift values are how much it is. Right. So for aromatic, it is 125 to 150 here. Isn't it? The aromatic carbon, means the carbon chemical shift value is 125 to 150. Now we'll see the means apply this particular the right calculation of these values for the aromatic compound. So here generally for the aromatic benzene, right, and the simple aromatic benzene, the chemical shift values of the carbon is 128.5 here for simple benzene, not substituted benzene. And if any substitution are there, then the value is going to increase here. For simple benzene, so here all the carbons will be showing the delta value of 128.5. Now, if any substituents are there, so you can add the values of that substituents which is mentioned in this group here. Okay, C1 ortho, right? So if the fluorine is present on ortho position here, then it is minus 12.9. If it is at meta position 1.4, if it is at para, minus 4.5 here. Okay, if fluorine, right? So if it is at on the C1 carbon, 6.2. If it is at ortho here, zero point 0.4. So like that, these are the values to add to the 128.5 here, right? The base value for this benzene, which is taken is 128.5, and based on the substituent and their positions, okay, isomeric positions like ortho, para, meta. So you can add the values as per this table. Okay, so if phenyl phenyl group is there, phenyl estate group is there, then the 9.1, it is C1 carbon, and at ortho it is 1.5. meta or minus 0.2 here, for para 3.8. So like that for amines. So the various possible substituents values are given in this particular table. Now we'll see one example here. Right, so here is a methoxybenzene. Now the base value which is taken 128.5 here, and the methoxy group is right present on the C1 carbon. Okay. Now the value is considered as a the methyl, which is the methoxy 31.5. Okay. So here the 128.5 plus 31.4 because it is on the C1 carbon. Okay. So we are adding this right. So this value to this one, then it becomes 159.90. Okay. So the C1 carbon, the value is right this one. It's C. Okay, C2 carbon here. Right. So for this carbon, the chemical shift value is this one. Actually, here 1, 2, 3, and 4 here. Okay. So this carbon is mentioned as 1 here in the ring. Right. So, but based on the non-equivalence of because this carbon also consider that's why the this is labeled as a 1 here. In general, the 1, 2, 3, 4. Okay. But as per the table, you take okay this that you take the value of the C1 carbon. So that is 31.4 here. And then it becomes 159.9. Now the C3 carbon here. Okay. So for C3 carbon, 128.5 and it is 14.4. The additional value here. Okay. So like that by adding all this one, right? Because here with respect to of this particular, okay. So with respect, right? So here, so with respect to of this carbon, okay. So this methoxy group is considered as a ortho, isn't it? This is considered as a ortho to this C3 carbon. That's why we are taking the minus 14.4. You can see the above table. And C4 carbon, right? So with respect to of this C4 carbon here, this methoxy substrate is considered as a this is ortho, this is meta. Then we are taking the one value and C5. For C5, the methoxy group is considered as a paras. This is adding the minus 0.7. The value is going to mention as 125. So the values of the substituted benzene. This paranite cyanide, okay, uh, paranitrile chlorobenzene, paranitrile chlorobenzene. So you can calculate the values here. Okay. And for the carbonyl compounds also, you can do the calculation as per that formula here. And the values are given here, right? So after calculation, you can compare the literature values. The aldehydes, it is 190 to 200, and for ketones, 195 to 220 here, and for acids, it is 165 to 185, right? So for nitriles, with cyanides, 115 to 125 here. So these are the chemical shift values, which is shown by this particular carbons here. Okay, so and all these are exercise, you can go through this particular exercise here, right? So I'm stopping here. Any doubt from this chemical shift calculation and coupling, right? Coupling homonuclear and heteronuclear couplings here. So in the next class, we discuss the applications of the C30 spectra, right? So generally, the the main application, right? The C13 spectra having uh, a very versatile applications here. Okay, so it will be applied in the reaction mechanism. It will be applied in the natural product chemistry here, right? And it will be applied in the structure determination. So in all the fields, the C13 spectra is very valuable. It is providing some valuable information, and it is having the application in all these fields here. So we'll discuss in the next class. Okay, I'm stopping here.
Okay, sir. Thank you.